Hey everybody, welcome back to Trigonometry. Today we're in section 5.3 and we're going to be learning about the sum and difference identities for cosine. So this section really focuses on two very important identities. We're going to learn the difference identity for cosine. That is, we're going to learn how to calculate the cosine of a difference between two angles. And we're also going to learn the sum identity for cosine, which is how to calculate the cosine of a sum of two angles. The difference identity for cosine leads us directly to the cofunction identities, and we have seen the cofunction identities in a previous section, but we'll look at them again because they are very closely related to the difference identity for cosine. And then we'll look at some application problems that use these two identities, and we will also verify some identities involving the cosine of a sum of two angles or a difference of two angles. So let's get started. First, let's write down these two new identities, or you could also call them these two new formulas. First, we have the cosine of A minus B. So A is an angle and B is another angle, and then A minus B is just the difference between those two angles. So this is why they call it the cosine of the difference of two angles. And the cosine of A minus B is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. While we're at it, let's go ahead and pick up the cosine of A plus B, and that's going to be equal to the cosine of A times the cosine of B minus the sine of A times the sine of B. Now you do not have to memorize these two identities, because these two will be on your formula sheet that you'll have access to during any remaining tests or exams in your course. But I do want you to notice that when we're calculating the cosine of A minus B, that formula has a plus sign in it. And when we're calculating the cosine of A plus B, that formula has a minus sign in it. That's a source of a lot of mistakes, because I think students want to assume that the formula for A minus B should have a minus, and the formula for the cosine of A plus B should have a plus. But that is not the case. So the signs are opposite here from what you might expect them to be. Now, please take a minute to understand this. We cannot distribute a function into its argument. A lot of students think that cosine of A minus B can be rewritten as cosine of A minus cosine of B, because what they're thinking is that we can distribute the cosine function. But please understand this. The distributive property is for multiplication. So you learned this in algebra. If you have an expression, for example, like this, where you have something like 2 times 3x plus 5, you know that you can do this multiplication by distributing the 2. So 2 times this quantity ends up being 2 times each term. 2 times 3x gives you 6x. 2 times 5 gives you 10. That is not what's happening right here. This is not cosine times A minus B. This is cosine of A minus B. So this cosine is not something that you can distribute. That's why we must use the formulas or identities that we saw right here. Now, one of the things we're going to be doing with these identities is using them as a formula for calculating the exact value of an angle. And in order to do that, we need to think of the given angle as a sum or difference of two angles whose exact function values we already know. So what angles do we already know the exact function values for? Well, those angles would be either 30, 45, or 60, or an angle that has one of these as a reference angle. Let's take just a minute to remember what all those angles are. So what we're going to do is go around the coordinate system and list every angle that has a 30-degree reference angle, every angle that has a 45-degree reference angle, and every angle that has a 60-degree reference angle. So let's start with 30. The quadrant 2 angle that has 30 as its reference angle is 150. The quadrant 3 angle is 210 degrees, and the quadrant 4 angle is 330 degrees. Now let's look at 45 degrees. The quadrant 2 angle that has 45 degrees as its reference is 135 degrees. In quadrant 3, it's 225, and in quadrant 4, it's 315. And then for the 60-degree angle, in quadrant 2, 120 degrees would have 60 as its reference. In quadrant 3, 240 would have 60 as its reference. And in quadrant 4, 300 degrees would have 60 as its reference. So when we're trying to write an angle as a sum or difference of two angles whose function values we know, we could use any of these numbers because we know the function values for all of these. So here's example 1, and it says find the exact value of each expression. In part A, we're asked to find the exact value of the cosine of 15 degrees. Now, we did not memorize the cosine of 15 degrees, so the way to come up with the exact value for this angle is to think of it as a sum or difference of two angles whose exact values we do know. One way to do this that comes to mind is to think of 15 as 45 minus 30. Now, you could just as easily think of 15 as 60 minus 45 and you would get the same answer. But here, let's think of 15 degrees as 45 degrees minus 30 degrees. And if we do that, then the cosine of 15 degrees can be restated as the cosine of 45 degrees minus 30 degrees. And now that we see it written in this form, we know that we can use our cosine of A minus B formula. And that looks like this. The cosine of A minus B is equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. So when we apply this formula, the 45 degrees will take the place of A, and the 30 degrees will take the place of B. So here we go. Cosine of 45 degrees minus 30 degrees is going to be cosine of 45 times cosine of 30 plus sine of 45 times sine of 30. And now we need to substitute in our known values. So the cosine of 45 degrees we know is the square root of 2 over 2. Cosine of 30 degrees we know is square root of 3 over 2. Then we have a plus sign. Then the sine of 45 degrees is square root of 2 over 2. And the sine of 30 degrees is 1 over 2. Okay, now we've basically got it, but we need to simplify it and put it in a nice form. So the first thing is that we need to multiply these two fractions together, and to do that we'll have to multiply these two radicals together. Now remember, when you multiply radicals, you just multiply what's under the radicals together. So square root of 2 times square root of 3 would be square root of 6, and in the denominator 2 times 2 is 4. Then for the second term, we have square root of 2 times 1, that would just be square root of 2, and in the bottom 2 times 2 again is 4. Now we have a sum of two fractions, and if these two numerators could be combined, we would be responsible for doing that. But you know that when you add two radicals together, in order to combine them, the numbers under the radicals have to be the same. In this case, these two radicals cannot be combined. So it would be acceptable to leave the answer in this form, but if you really wanted to write it as one fraction, you would just put square root of 6 plus square root of 2 all over one single denominator, which would be 4. So it's fine for you to leave the final answer in either form. Neither one is better than the other, but you might see either one on a test or a quiz, so you need to be familiar with both. Now, let me caution you about one thing that I very frequently see students do. I very often see students get the first step of the problem correct, but then when they go to substitute in their known values, instead of saying that the cosine of 45 degrees is square root of 2 over 2, they'll say the cosine of 45 degrees is the cosine of square root of 2 over 2. And then they'll do that for each function value that they're substituting for. And at this point, they're stuck. Now, why is this wrong? Because the cosine of 45 degrees is not the cosine of square root of 2 over 2. You're not substituting square root of 2 over 2 in place of the 45 degrees. You should be substituting square root of 2 over 2 in place of the entire cosine value. So that is completely incorrect. The cosine of 45 degrees is square root of 2 over 2, period. And the cosine of 30 degrees is square root of 3 over 2. And then you know the rest. But think about the difference here and avoid this mistake. Do not make this mistake. When you substitute your known values in place of each function, that value replaces the entire function, not just the angle. Now let's look at example 1 part B. So here we're asked to find the exact value of the cosine of 5 pi over 12. Now we know that we need to think of 5 pi over 12 as a sum or difference of two angles whose function values we know, but it's hard to do that when the angle is written in radian form. So I think the easiest thing to do is to convert 5 pi over 12 radians into degrees, and we know that we can do that by replacing the pi symbol with 180 degrees. So 5 pi over 12 radians is the same as 5 times 180 degrees over 12, and when you get that, you find out that that is equal to 75 degrees. Now, how can we break 75 degrees down into two angles whose function values we know? I don't think you'll have any trouble coming up with 30 plus 45 degrees. Now, somebody might say, why could we not use 60 plus 15? The answer to that is you could use 60 plus 15 if you knew the exact function values for 15 degrees, but we don't. So we always want to break our angle down into two angles whose function values we already know. Okay, now when we go to apply our formula, we're going to say that the cosine of 5 pi over 12 is equal to the cosine of 75 degrees, but we're going to write it as the cosine of 30 plus 45 degrees. So this lets us see our A and our B. And of course, the plus sign here tells us that we need to use the cosine of A plus B formula. So let's take a look at that. Okay, this is the formula that we're substituting into. The 30 degrees is our A, and the 45 degrees is our B. So it's going to be cosine of A, which is 30 degrees, times cosine of B, which is 45 degrees, then minus sine of 30 degrees times sine of 45 degrees. And so now we've used our formula, and the next step is to substitute our known values in place of each function value. So we know that the cosine of 30 degrees is square root of 3 over 2, and that's supposed to be times the cosine of 45 degrees, which is square root of 2 over 2. Then we have a minus sign, and then the sine of 30 degrees is 1/2, and the sine of 45 degrees is square root of 2 over 2. Okay, now again, multiply your two fractions together, top times top and bottom times bottom. So square root of 3 times square root of 2 is square root of 6. In the bottom, 2 times 2 is 4. Then you have a minus sign, and then 1 times square root of 2 is square root of 2, and in the bottom, 2 times 2 is 4. And so this time we've come up with square root of 6 over 4 minus square root of 2 over 4. And just like we saw in part A, it's fine to leave this answer in two terms, or if you really want to, you can combine them into one fraction by saying square root of 6 minus square root of 2 all over 4. Either way is acceptable. Now, it's really not a coincidence that we ended up with the same numbers here that we saw in part A, because after all, we used the same two angles in our formula. And that's going to happen a lot. What will mostly change here will be the signs of the terms. So we could have come out with a negative square root of 6 or a positive square root of 2. You don't know until you work the formula what the signs are going to be, but pretty much the numbers that you'll see in most of these are these numbers, because everything we're going to do is related to these two angles, or maybe 60 degrees, which, shares the same function values as well. And here in part C, we're asked to find the exact value of the cosine of 345 degrees. So obviously this is way bigger than any combination of 30, 45, or 60 could give us. So we need to think of some angles that are related to 30, 45, and 60. There are several combinations that you could choose from here, but the one that I see right off the bat is that 345 degrees can be broken down into 300 degrees plus 45 degrees. Now, why did I choose 300? Because it has a reference angle of 60, so I know the exact values for 300. We also could have gone with 315 plus 30. That would also add up to 345, and there are lots of others. But you just choose the one that is the most obvious to you, so that's what I've done here. And then we can write cosine of 345 degrees as cosine of 300 degrees plus 45 degrees. Okay, now this tells us that we want to look at our cosine of A plus B identity. So I've copied that for you here. Remember, you'll have your formula sheet that you're looking at, so you will copy this straight off the formula sheet. And now let's plug into this formula using 300 degrees in place of the A and using 45 degrees in place of the B. So cosine of 300 degrees plus 45 degrees is equal to cosine of 300 degrees times cosine of 45 degrees minus sine of 300 degrees times sine of 45 degrees. And now we need to substitute in our known values, but of course you might not have the values for sine and cosine of 300 degrees right off the top of your head. Let's draw ourselves a diagram, and remember that a 300 degree angle is in the fourth quadrant. It will have a 60 degree reference angle. So the sine of 300 degrees is going to be the same absolute value as the sine of 60 degrees, but sine values are negative in the fourth quadrant. So the sine of 300 degrees is going to be negative square root of 3 over 2. And then the cosine of 300 degrees, we remember that cosine values are positive in the fourth quadrant, so this is going to be the same as the cosine of 60 degrees, which we know is 1/2. And now we're ready to substitute our known values into our formula. So the cosine of 300 degrees is 1/2. The cosine of 45 degrees, we know by heart, is square root of 2 over 2. Then we have a minus. And then the sine of 300 degrees is negative square root of 3 over 2. And the sine of 45 degrees, of course, is square root of 2 over 2. And now, just like we've done in the last two examples, when we multiply these first two fractions together, we get square root of 2 over 4. And now this minus and this negative go together to make plus. And then we have square root of 6 over 4 as our second term. And of course, that can be written as a single fraction, square root of 2 plus square root of 6 all over 4. And now for part D, we're asked to find the exact value for the cosine of 165 degrees. Now again, there are a number of ways that you could break 165 down. The first way that pops into my head is to think of it as 120 degrees plus 45 degrees. So we're going to write that the cosine of 165 is equal to the cosine of 120 plus 45 degrees. And so now we can see that we want to use our cosine of A plus B formula. Let's take a look at it here, just copied straight off the formula sheet. And now we're going to substitute into this formula, putting 120 degrees in the A position and 45 degrees in the B position. So we're going to have cosine of 120 degrees times the cosine of 45 degrees minus the sine of 120 degrees times the sine of 45 degrees. Now, of course, in order to substitute our known values in here, we need to think about what the cosine and sine of 120 degrees would be. So let's draw ourselves a little diagram here. Of course, you know 120 degrees is in quadrant 2, and it's going to have a 60 degree reference angle. So now the sine of 120 degrees is going to be positive because it's a quadrant 2 angle, sine of 60 degrees, which is square root of 3 over 2. And then the cosine of 120 degrees is going to be negative because cosines are negative in quadrant 2. And then the cosine of 60 degrees is 1/2. So the cosine of 120 degrees would be negative 1/2. Now let's substitute our known values into the formula. The cosine of 120 degrees we replace with negative 1/2. Cosine of 45 degrees we know is square root of 2 over 2. Then we have our minus sign. Then the sine of 120 degrees is square root of 3 over 2. Sine of 45 degrees we know is square root of 2 over 2. And now multiplying the fractions together, we end up with negative square root of 2 over 4 minus square root of 6 over 4. As always, it's fine to leave it in this form, but if you wanted to combine it into a single fraction, that would be negative square root of 2 minus square root of 6 in the top, all over 4. And I do want to point out to you here that this negative is attached to this radical. It should not be in front of the whole fraction, because if you put it there, you would be affecting all the signs in the top, and that would also change this sign. But it needs to be negative square root of 2 minus square root of 6. Okay, now here is example 2. We're still using the same identities here, but now we're going to use them a little bit differently. So the instructions say use a sum or difference identity to find the exact value of each expression. Now you might be thinking, couldn't I just plug these into my calculator? And yes, you could, but if the answer turns out to be square root of 3 over 2 or something like that, your calculator won't help you because it's going to give you a decimal value. We need an exact value. So instead of going to the calculator, let's try comparing this expression to either cosine of a minus b or cosine of a plus b. Now if you think about our two formulas that we have available to us, we have 87 degrees in the A position and 93 degrees in the B position. And the minus here tells me that the formula that's been used is the cosine of A plus B formula. So all of this is going to be equal to the cosine of 87 degrees plus 93 degrees. Now that we have those two angles in the same parentheses, we can add them together. 87 degrees plus 93 degrees is 180 degrees. So now we can write this as the cosine of 180 degrees, which we do know how to figure out without the calculator. So 180 degrees, of course, would be on the left side of the unit circle. It goes through the point negative 1, 0, so the cosine of 180 degrees we know is negative 1. And now for part B, we have cosine of 307 degrees times cosine of 67 degrees plus sine of 307 degrees, sine of 67 degrees. Now this time the numbers in the A and the B positions are 307 degrees and 67 degrees, but this time there's a plus sign in between the two terms, so that tells us that the identity that's been used here is the cosine of A minus B, where the A number is 307 degrees and the B number is 67 degrees. So this can be restated as cosine of 307 degrees minus 67 degrees. Now that we have these two angles in the same parentheses, we can do this subtraction. 307 minus 67 is 240. So all of this is just going to be equal to the cosine of 240. Now we know 240 degrees would be a third quadrant angle, and we know it would have a 60-degree reference angle. And we also know that cosine values are negative in quadrant 3. So the cosine of 240 is going to be negative cosine of 60, which is 1/2. So the cosine of 240 degrees is negative 1/2. Now we're going to switch gears a little bit and talk about the cofunction identities. So we're going to derive the cosine of 90 degrees minus x equals the sine of x. And we've seen this identity before, but this time we're going to use our cosine of A minus B identity to get there. So if you look at cosine of 90 degrees minus x, you can see how this fits our formula for the cosine of A minus B. So we will use that cosine of A minus B formula, but we'll plug 90 degrees in place of the A, and we'll plug x in place of the B. So that's going to make cosine of 90 times cosine of x plus sine of 90 degrees times sine of x. Now 90 degrees is a quadrantal angle, so of course we know the values for the sine and cosine of 90 degrees. Let's remember that the terminal side for a 90-degree angle goes through the top of the unit circle, so it goes through the point 0, 1. So the cosine of 90 degrees is 0, and the sine of 90 degrees is 1. Okay, over here, substituting our known values, cosine of 90 degrees is 0, so we have 0 times the cosine of x, and then plus sine of 90 degrees times sine of x will be 1 times the sine of x. Now, of course, 0 times anything is 0, so that term will disappear, and then the second term is 1 times sine of x, so that's just sine of x. And so here we have the identity, the cosine of 90 degrees minus x equals sine of x. And you'll remember that's one of our cofunction identities that we saw earlier in the course. So now we won't derive the rest of them, but we did just derive that cosine of 90 degrees minus theta is equal to the sine of theta. And so we see that cofunction relationship. if the cosine of 90 degrees minus theta is equal to sine of theta, then that means the sine of 90 degrees minus theta is equal to the cosine of theta. And the tangent of 90 degrees minus theta would be equal to the cotangent of theta. Cotangent of 90 degrees minus theta would be equal to tangent of theta. Secant of 90 degrees minus theta would be equal to cosecant of theta. And cosecant of 90 degrees minus theta would be equal to secant of theta. And of course, all of these identities are written in terms of degrees, but you could get the same identities in radians by replacing 90 degrees with pi over 2 radians. So instead of memorizing 6 separate identities, I would really like for you to understand that there's one principle behind all 6 of these. A function for any angle is equal to the cofunction of the complement angle. You know that for any angle theta, we can calculate the complement of that angle by calculating 90 degrees minus that angle. For example, the complement of 30 is 60 because 90 degrees minus 30 is 60. Okay, let's look at a couple of others and make sure that that principle holds up. The cotangent of theta should be equal to the cofunction of the complement angle. So the cofunction for cotangent would be tangent, and the complement angle for theta would be 90 minus theta. Over here on this last one, the secant of theta should be equal to the cofunction of the complement. Well, the cofunction for secant is cosecant, and the complement angle for theta is 90 minus theta. So you see, all 6 of these identities are really just all based on one idea. So now let's practice using these cofunction identities in example 3. The instructions say find one value of theta or x that satisfies each of the following. In part A, we have cotangent of theta equals tangent of 25 degrees. Now, if you wanted to do this using the identities, you might look at your set of cofunction identities and you probably would choose to use the one that shows cotangent of theta. And that identity looked like this. The tangent of 90 minus theta equals the cotangent of theta. Okay, now you can see that the left side of the problem equals the right side of our identity, and we have tangent of 25 degrees equals tangent of 90 degrees minus theta. So now you could say, okay, I see that 90 degrees minus theta is equal to 25 degrees, and you could write that as an equation and then solve for theta. So of course you'd have to add theta to both sides to move it over here, and you'd have to subtract 25 from both sides to move it over to the left, and you'd end up with 90 degrees minus 25 degrees equals theta, and so you would see theta equals 65 degrees. Now you can do it that way, but I'm going to tell you that I don't think that's the easiest way to do it. What I would rather you do is focus on the principle behind the identities. So let's start over. Let's think of it this way. If the cotangent of an angle is equal to the tangent of 25 degrees, we know that cotangent and tangent are cofunctions. That means that theta and 25 have to be complement angles. Well, if theta and 25 degrees are complements, that means that theta plus 25 is 90, and that means that theta is 90 minus 25 degrees, or 65 degrees. To me, that is an easier way to come at it rather than you trying to fit what you have here into one of your identities. So let's try that strategy on part B. So here it says the sine of theta is equal to the cosine of negative 30 degrees. Well, sine and cosine are cofunctions, and that means that theta and negative 30 are complements. So theta plus negative 30 has to be 90. Now if we just add 30 to both sides of our little equation here, we can see that theta is going to have to be 120 degrees. And let's try that on part C. So here we have cosecant of 3 pi over 4 equals secant of x. So first we notice that cosecant and secant are cofunctions. That means that 3 pi over 4 and x are complement angles. Now this is in radians, and you could convert it to degrees and then convert back to radians at the end, But I think this is simple enough that we'll just stay in radians here. So if 3 pi over 4 and x are complements, that means that they have to add up to 90 degrees, but in radians we would say that they add up to pi over 2 radians. So we have x plus 3 pi over 4 equals pi over 2 radians. Now to isolate the x, we subtract 3 pi over 4 from both sides, and then we have x equals pi over 2 minus 3 pi over 4. Now, of course, we would want to get a common denominator here, so we would multiply this first fraction by 2 over 2. That would give us 2 pi over 4 minus 3 pi over 4, and that's going to be negative pi over 4. Now, you know from previous experience that if you don't want to subtract the fractions by hand the way I did here, you can just do 1 over 2 minus 3 over 4 on your calculator. You'd get negative 1/4, and then you'd just put the pi symbol back in at the end. And so that's example 3. Now here in example 4, we're doing a very similar thing, only they've said write each function value in terms of the cofunction of a complementary angle. Now we know how to find the cofunction of any function. It's always just a matter of either adding the co-prefix or taking it away. And we know how to find the complement of any angle. It's always just 90 degrees minus the angle that we're working with. So here in part A, where we have cosecant of 14 degrees and 24 minutes, in order to write this as the cofunction of a complementary angle, we know that the cofunction for cosecant is just secant. And we know that the complement of 14 degrees and 24 minutes is just going to be 90 degrees minus 14 degrees and 24 minutes. Now you can do this subtraction on your calculator, and then we would have secant of 90 degrees minus 14 degrees and 24 minutes is equal to secant of 75 degrees and 36 minutes. And that's all we were asked to do. Notice it said write each function in terms of the cofunction of the complementary angle, and we've done that. And then in part B, the same thing. Here we have the sine of 142 degrees and 14 minutes. So if we want to write this in terms of the cofunction of the complementary angle, we know that the cofunction for sine is cosine, and we know that the complementary angle is 90 degrees minus this given angle. So 90 degrees minus 142 degrees and 14 minutes. Okay, do the subtraction on your calculator, and then you'll have the cosine of this difference is equal to the cosine of negative 52 degrees and 14 minutes. And so we've restated this sine function in terms of the cosine of the complement angle. And here's a little application problem for us. This is example 5. It says suppose that the sine of s is 3/5 and the cosine of t is negative 12 over 13. And both s and t are in quadrant 2. Find the cosine of s plus t. Okay, now I always like to think of this in terms of a recipe. You know, if you wanted to make something at home, like, for example, chocolate chip cookies, you would get yourself a chocolate chip cookie recipe, and then you would look at all the ingredients. And for each ingredient, you would either say, I have that already, or I don't have that, and I need to go to the store and get it, right? So you can't make your recipe until you have all the ingredients. And that's what this is. A formula is basically a recipe. Let's look at the recipe or the formula for the cosine of s plus t. This is just going to be our identity for the cosine of a plus b, but we've got s and t in place of a and b. So let's just write it down straight off the formula sheet. The cosine of s plus t would be cosine of s times cosine of t minus sine of s times sine of t. So we have 4 ingredients in this formula. Some of the ingredients we know already, and some of them we don't know. We'll have to go find out what they are. So let's see what we have and what we don't have. Do we have the cosine of s? Well, if you look up here at the values we were given, we do not have the cosine of s given to us in the problem. So let's leave that blank just for a minute. Do we know the cosine of t? Well, yes, cosine of t was given to us in the problem, so we'll replace cosine of t with negative 12 over 13. Then we have a minus sign. Our next ingredient is the sine of s. Do we know the sine of s? Yes, that was given to us in the problem. So we will replace sine of s with 3/5. And then our last ingredient is the sine of t, and we were not given that in the problem, so we'll just leave a blank for that one as well. Now, we don't know these two numbers yet, but we do have enough information to find out what these numbers are. What we'll have to do is draw a diagram for angle S and draw a diagram for angle T and figure out these two missing values by using the values that we were given. Let's start with angle S. We know it's a quadrant 2 angle, and if we draw our little dotted line down to the horizontal axis, and remember that the sine of S is 3 over 5, we know that the definition for sine was y over r, so the vertical side of our triangle is 3 and the hypotenuse is 5. And in order to figure out what the cosine of this angle is, we just need to figure out the length of the horizontal side. Now you might recognize this as a 3, 4, 5 triangle, but even if you didn't, you would subtract the squares to get this missing side. So the square of 5 is 25, and then the square of 3 is 9. 25 minus 9 is 16, and the square root of 16 is 4. So the length of this missing side is 4. Now we know that the cosine of S is going to be negative because S is a quadrant 2 angle, and then the x over r gives us 4 over 5. Let's do the same thing for angle T. Now we're told that angle T is also in quadrant 2. So I've drawn a quadrant 2 angle, and now I'll close up my triangle here. And they told us that the cosine of T is negative 12 over 13. Now we know it ought to be negative because T is a quadrant 2 angle, but the 12 over 13 represents x over r. So the horizontal side is 12 and the hypotenuse is 13. Now to find the vertical side, we need to subtract the squares. 13 squared is 169. 12 squared is 144. 169 minus 144 is 25. So the length of the vertical side is the square root of 25, which is 5. Okay, now the sine of angle T is going to be positive because sine values are positive in quadrant 2, and it's going to be y over r. So it's going to be 5 over 13. Okay, now we have all our ingredients plugged in, and all that's left is to evaluate. So let's start by multiplying the first two fractions together. For negative 4/5 times negative 12 over 13, we're going to multiply top times top and bottom times bottom. Negative 4 times negative 12 is 48. In the bottom, 5 times 13 is 65. Now we have a minus sign. And then we'll multiply these last two fractions together. Top times top gives us 15. Bottom times bottom gives us 65. Now I know some of you would notice that the 5's would reduce, leaving you a reduced answer of 3 over 13 for this second term, and that is true, but notice that if I do that reducing, I will lose my common denominator, and I need that common denominator to finish the problem. So it's really not in your best interest to reduce on this step. Just keep your common denominator here, then do your addition or subtraction, and get your final answer. At the end, if you can reduce, then you can do it. Here we have 48 over 65 minus 15 over 65. 48 minus 15 is 33. So our final answer is 33 over 65. And again, if this fraction could be reduced, we would be responsible for doing that. This is what I call an S&T problem for obvious reasons, and you can pretty much count on seeing an S&T problem on your test if you're taking trig in the regular classroom with me, or if you're taking the course online, plan to see an S&T problem show up as a show work problem on your quizzes and exams. Now here in example 6, the instructions say write cosine of 180 degrees minus theta as a trigonometric function of theta alone. This is one of the absolute easiest problems in this section, but a lot of students miss these, and I believe it's because they don't understand what the instructions are asking them to do. To write this expression as a function of theta alone, we've got to separate the 180 degrees from the theta. And of course, our cosine of a minus b identity will help us do that. We just need to apply the identity here. So if we think about restating cosine of 180 degrees minus theta using our cosine of a minus b formula, we'll have the 180 degrees in place of the a, and we'll have theta in place of the b. And that would give us cosine of 180 degrees times cosine of theta plus sine of 180 degrees times sine of theta. And now all that's left is to plug our known values in here. So let's think about a 180 degree angle. That would be a quadrantal angle whose terminal side goes through the point -1, 0. So the cosine of 180 degrees is going to be -1. So we have cosine of 180 degrees is -1, and that's multiplied by cosine of theta. Then we have plus the sine of 180 degrees, which would be 0, times the sine of theta. Now simplifying here, we know that 0 times anything is going to be 0, so that term disappears, and we have -1 times cosine theta, which is just negative cosine theta. And so you see that we restated this original cosine function as a function of theta alone. And again, anytime they ask you to write an expression as a function of theta alone, it's just going to be a matter of applying your a minus b identity or your a plus b identity. Now let's look at a couple of proofs together. In example 7, it says verify that the cosine of 270 degrees plus x is equal to the sine of x. Now you remember verifying from our previous section, and you know that when we verify an identity, we choose which side we want to work with and we copy down that side, and then we either use identities or algebra to simplify until we can make the side we're working with look like the other side. Now you'll remember that we always started with the more complicated side. Here I think you can see that the left side is more complicated than the right side. So we'll start with our cosine of 270 degrees plus x. This clearly looks like we could apply our cosine of a plus b identity with the 270 degrees in the a position and the x in the b position. So let's do that. Just copying your cosine of a plus b identity right off your formula sheet, you would get cosine of 270 degrees times cosine of x minus sine of 270 degrees times the sine of x. And you remember that we always had a vertical line, and then on the right side of our proof we always said what kind of identity we used. So here I've just written down that I used the cosine of a plus b identity for that. Now what can we do next? The only thing we can do now is substitute the known values for sine and cosine of 270 degrees. So let's remember that a 270 degree angle would have its terminal side pointing down. So it's going to go through the point 0, -1. And that means the cosine of 270 is going to be 0. So we have 0 times the cosine of x minus sine of 270 degrees, which would be -1, times sine of x. Okay, and over here on the right, I'll just say that I substituted my known values. Now we know that 0 times anything is 0, so that term is going to go away. And then minus -1 sine of x simplifies to positive 1 sine of x. Over here on the right side, I'll write down that I simplified. And of course, 1 sine of x is just sine of x, which is a match for the right side of our identity, so we know that we're finished here. And here's part B of example 7. You might feel like pausing the video and trying this one on your own. And so now if you've had a chance to do that, let's go through this together. It says verify that the cosine of pi over 2 plus x is equal to negative sine of x. So essentially we know that we're going to apply our cosine of a plus b identity to the left side here, and by the time we get finished simplifying, we should come up with negative sine of x, right? We just have to show the steps, because when you verify or prove an identity, You just have to show that one step leads to another and gives you the result that's on the other side. Okay, so let's start with our cosine of pi over 2 plus x. Now, the only thing that we can really do to this expression is apply our cosine of a plus b formula to it. So that would be cosine of pi over 2 times cosine of x minus sine of pi over 2 times sine of x. Over here on the right side, let's say that we used our cosine of a plus b identity. Now the next thing we need to do on the left is substitute our known values in here. So we want to remember that pi over 2 radians is equal to 90 degrees. And of course the terminal side of a 90-degree angle points straight up, so it goes through the point 0, 1 on the unit circle. So the cosine of pi over 2 will be 0, and then we have times cosine of x minus sine of pi over 2, which we know is 1, times sine of x. And over here on the right, we'll just state that we substituted our known values. Now we know that 0 times the cosine of x is going to be 0, and negative 1 sine of x is going to be minus 1 sine of x. Over here on the right side, let's state what we did, which was to simplify our expression. And now we know that negative 1 sine of x is just negative sine of x, which is an exact match for the right side of the identity we're trying to prove, so we know that we're finished here. And finally, here's our last proof together for this section. This is example 8. It says verify that the cotangent of x minus the tangent of y is equal to the cosine of x plus y all over sine of x times cosine of y. Now, as always, when we're doing a proof, we have to decide which side of the equal mark we want to work with. And we have always said we start working with the side that looks more complicated than the other. And I think for us this time it's the right side that looks more complicated than the left side. And also I like the idea of working with the right side because I see this cosine of x plus y in the top of the right side, and that gives me an idea of what we could do for our first step. So let's go ahead and copy down that right side. And now let's make a vertical line so we can have a place to write our explanations on the right side. And now when you look at the top of this expression, we said that it's the cosine of x plus y. So we can see that we can use our cosine of a plus b identity here, where the a will be replaced by x and the b will be replaced by y. So let's do that, but first I'm going to copy down our fraction bar and the denominator of our expression because that's not going to change. Now in the top, cosine of x plus y can be rewritten as cosine of x times cosine of y minus sine of x times sine of y. Over here on the right, let's state that we used that cosine of a plus b identity. Now when we were in section 5.2 and we were learning how to do proofs, we always said, if you don't know what to do next, look at what you've got and look at what you're trying to get to. The expression on the left side of our equation has two terms, so it would be a good idea for us to create two terms here as well. Let's use that strategy of splitting the fraction. So I'm going to restate this single fraction as two separate fractions, and they both will have the same denominator that we see here. So that's going to give us cosine of x times cosine of y over sine of x times cosine of y, then minus sine of x times sine of y over that same denominator. Over here on the right side, let's write down that we split the fraction. Once you split the fraction, you can reduce each fraction separately. In the first term, we see that we have cosine of y in both top and bottom, so those will divide out. In the second term, we see that we have sine of x in both the top and the bottom, so those will divide out. Over here on the right side, let's state that we reduced. Now if we look at what's left in the first term, we see cosine of x over sine of x. We know that we can use a quotient identity to restate that as cotangent of x. Then we have our minus sign. Over here in the second term, what's left is sine of y over cosine of y, which we know can be restated as tangent of y. And what kind of identities did we use to restate both of those? Those were quotient identities, so we write that over here on the right side. Now notice that what we've ended up with here is an exact match for what we wanted, and so that proof is finished. Okay, everybody, that's it for section 5.3. I'll see you again in section 5.4, where we will learn the sum and difference identities for sine and tangent, and we'll see a lot of the same types of problems that we saw in this section. See you then. Bye-bye.